Now, okay. So we're trying to understand why linear and angular momentum are not the same thing in quantum mechanics.
Yeah. This is from, this stemmed from a question that Pradyot had regarding how angular momentum would come into the picture of path integral. Was that the question? Or?
Yeah, so basically the question was, so you have path integrals and payment diagrams or things like that, which can be visualized as some sort of linear propagation or whatever, right? But when you try to switch it to the angular scheme of things, the whole picture becomes some sort of a little different. I had in mind, because you have some kind of periodicity which you don't have for classical free propagation. So yeah, we're just trying to understand, like, just play around with these two concepts and see where it goes.
Okay.
PPK. Okay.
I have my Kronecker deltas. You will see that we'll get a contraction. Things will look pretty neat, but it's just a matter of making sure that we get the minuses right. IP. So you see what we have here. So the first thing is going to contract I with P. Second thing is going to contract J with K. So you have two options. So if I wanted to make this into one term, I would rather have the same order index contract the same order index. I said that in a weird way, but basically what I'll do is I'll take this MIK LJP, and then I have a KJ, right? So last with second, I'll swap these so that it's last with last. And then what do I get? Epsilon, epsilon. You have these annoying identities.
Yeah.
You'll get commutator of deltas. And then I'll do the same thing here. I'll get an IAP, which again, see, well, first with last. So I can swap these so that it's last with last. And then it's the same. It's a minus sign. And then I get a commutator. In all, I'll just get another epsilon's worth of, so I end up getting the equivalent of another epsilon. Because epsilon ijk, you can realize this multi-commutator mess. And this is an exercise for people watching the relevant. Let me just make sure that in hindsight I get the right components. So what are the three indices here? I, K, so M and L, right? So I have M, L, J, we can call it whatever we want now. Right. Those are three. Times J sub J, where you see there's just a lot of rewriting, so you have to do this kind of exercise. The J sub J is given by epsilon. So in Cartesian coordinates, I'm not too concerned about whether I have raised and lowered or lowered and raised, because the Kronecker delta comes with no components that I have.
Isn't with
L. So you see, I take these two epsilons and then I sort of distribute them between the terms. Right? I can take this one epsilon inside and the other epsilon inside with a minus. So I could either do the delta-delta trick, or I could just do it this way. And honestly, I think this is a much easier way to see the result. So in the end, what did we discover? Well, we discovered that JJ Matrix I. Minus. Right? So angular momentum doesn't commute with itself, unlike the components of linear momentum. So it's different because it's a composite operator formed from X and P.
Right.
See? So let's just, pay attention to these two and this, which also means that the components of angular momentum, you can choose which one you want to diagonalize. This is what you normally do when you talk about spin and quantum mechanics.
Yeah.
The convention is to take J, the Z component of J, right? Call it, sorry, let me do that more slowly. I say that J is Z of J. Yeah. This is my quantization rule. But now you see that Jx and Jy won't maintain this.
Right.
So what will happen, and this is what your quantum mechanics education can hopefully teach you, is that Jx and Jy form these sort of ladder operators.
Right.
So when this acts on J, for the life of me, can't remember, there's some square root, and then there's some stuff. But really, what will happen is that it'll be equal to some function J times 1.
Yeah. Okay.
And you'll find that the minus sign, the other thing happens. So this is some other function.
So yeah, basically what it's something like saying whatever happens in the X and Y axis gets translated onto the Z axis, creates some sort of a ladder operator on the Z axis.
Yeah, so the point is that they don't commute.
It's like, okay.
So they don't commute, but you know what does commute? So this is still true though. Commutator between J sub Z and
Yeah. Okay.
And so what you have, so this is one of the most horrendously explained concepts in 11th grade chemistry or something. Or 12th, I don't remember, but I remember this being particularly bad. So hopefully nobody remembers what that was. But yeah. So that's called the quadratic Casimir. Anyway, this is rudimentary SU2 representation here. Why SU2? Because it's SO3, because it's the rotation group. So this is, all that to say that spin in quantum mechanics is fascinating. Angular momentum in quantum mechanics is a fascinating thing.
Okay, just hold on a second. I'll just take a screenshot of the whole thing.
Sure.
Documentation.
I can send you this, by the way. It's way easier. Like I can send you whatever format you like. Like this kind of worksheet.
Okay.
Really.
Yeah, we can actually include it as a part of the description in the video.
Oh, for sure, yeah. So now, in terms of what you've just seen, can you rephrase your question? If you want to, or if there's a question.
I mean, that's fine.
No, yeah. Okay. Yeah.
So, okay, if you wanted to play this whole game, in the path interval. This is another thing you can try. What would you have to establish? Like, what's the most crucial thing to get to this? You see, this is the most important line. This thing here, this last line. Once you're there, you can work out everything else. So once I have this commutation relation, I diagonalize one of them, JZ, and then I work out the commutation relation between everything like JZ and just J plus and J minus, as they're called. And then I can derive what Fj and Gj are.
Right.
Usually there's some square roots and other such things, but you can work it out. Well, actually, sorry, I made a complete mistake here. This is not, let's call this, so there's a J and then there's an M. Okay, so this is usually labeled by two things, J and an M. J is always the same.
I mean, you could use Noether's theorem, right? From the charge.
Yeah, but all I'm saying is that if your charges form a, like, you know, an algebra.
Oh, right.
Okay, great. Sorry. You call the angular momentum Jz's eigenvalue M. And then there's this additional seemingly nebulous J, which is telling you what the total angular momentum really is, right? Because it's labeling my J squared. Right? So the big J is this J is a label of J squared, M is a label of JC. And then M you can climb up or climb down, if you know what is Fj and Fj. But you can't change J with Jz. So you can only change M. Similarly, you can't change M with J squared. These are two different things. They just move each other. Sorry about that, but that's how SU2 representation works. And there will basically be, within any given J, 2n plus 1 states that you can climb or climb up or climb down.
Right.
So n is like your oscillator number. J is an additional label.
Yeah.
So J is like the total number of particles, if you like. It's related to that. Whereas, you know, M is which excitation you're in. Yeah.
Okay, that was that's for me. Also lately, I've been trying to understand how supersymmetric gauge theories work.
Okay.
I think I don't know if I read the chats wrong, but I think Pradyo was talking about something similar, or maybe something different. I don't know.
I understand very little about how they work in general.
I see.
But
Okay.
I mean, we can still muse about them.
Yeah, very little though. Yeah, or we could talk about something else as well.
Oh yeah, I mean it's just subjective, right? So you could say how many dimensions? 4,
2,
3,
yeah.
2.
What have you?
I don't know. There's super Yang-Mills in 2 dimensions.
I see.
That's in theory, but actually there's a lot that can happen in that theory.
Yeah, like I mean, if you have more than 3 parameters playing around, you can have any kind of combination of things that commute and don't commute, right? So, right now it is 2, and then you have rotation is basically like you have 2 that commute and one that doesn't.
You mean the composite operator?
Yeah.
I see.
Yeah. So if you have n dimensions, if you generalize it, you don't know what permutation and combination will work. So what exactly is rotation in n dimensions is something that we might have to ask. But So yeah, I mean,
It's not that complicated. So this exercise that you do in group theory too, or in the representation theory of SU2, it's a nice one. And actually, there's a way in which you can. Okay, how should I put it? There's a notion of these root systems and other
Right.
such things in the
Yeah,
representation theory, where you find SU2s within, you find SU2 representations within whatever representation, so semi-simple Lie algebra that you're looking at.
Right.
And there, yeah, you have multiple SU2s essentially, and you can use that to build up the bigger representation. There's going to be differences though. So what happens in higher dimensions is that you don't necessarily have a relationship between unitary and orthogonal group. So it's not always going to happen. It'll happen in odd dimensions, and even dimensions, it's just a little bit different. And it's fine though. You can still work out the representation theory. There's rules for that. So when you say that which combination would work, you're guaranteed that there's going to, okay, so the feature that there's going to be some operator that will commute with every operator is a feature called having a center of the Lie algebra. And this is what's called the quadratic Casimir here. And for other groups, you have other Casimirs. So for the Poincare group, for instance, you have two Casimirs. One is quadratic. Are they both quadratic? No. There's something called a Pauli-Lubansky vector. And then there's the square of that. So it's quadratic in this Pauli-Lubansky vector, but that thing itself depends on momentum. And you have t squared, the momentum squared. Mass and spin, roughly speaking, come from those two Casimirs. So if you have an irreducible representation, then the eigenvalues of the Casimirs, what you are also guaranteed is that the Casimirs are proportional to identity. So you can label irreducible representations with the eigenvalues of the Casimir operator. And yeah, so there's a lot of tricks that people can use if they really wanted to play any of these games. So you might deal with higher dimensional rotation groups even if you're in 4 dimensions. So 3 space and 1 pen dimension.
Yeah.
And that would be in the case where you're dealing, for instance, with de Sitter or anti-de Sitter.
Right.
So
right.
When you have de Sitter space, you can actually think about it as embedded in some higher dimensional space.
Right.
Where you have the following hyperbola.
Right.
So in this 5-dimensional flat space, de Sitter is the following hyperbola, or this hyperbola, exactly what you call it.
Right.
And here you actually find that the analog of the rotation group becomes the de Sitter group. So the analog of the Lorentz group becomes the de Sitter group.
Oh, okay.
Right. So
does that come to be?
Group, and the reason for that is, so yeah, maybe this is something that you can use about
Yeah.
So let's do something different in two ways.
Mm.
First, let's take Euclidean signature.
Right.
And then let's say that I have xi equals 1. This defines a unit sphere.
Right. Right.
So what is the isometry group of this surface? The rotation group. It's just going to
The
be
rotation group. Yeah. Yeah. Okay.
Yeah. So you see, if I ask about the isometry group, that is the group that will preserve the group of transformations that will preserve the surface, then I get the rotation group.
Right.
Now, let's say that I have Lorentz signature.
Right.
Then I'm going to have signature. I'm going to have the following equation. And what's the group that will preserve this? Well, that would be the Lorentz group.
Right.
So it's just essentially just a different signature rotation group. And so that's the sense in which, okay, but where do you actually see this? Like, what's an example? Where do you actually see this? Well, let's, instead of this x, let's write p, just for notational ease. Right? So basically, if I multiplied everything by m,
yeah,
that's an m squared. You see, it's the same reason that you have Lorentz transformations respecting the mass energy relation.
Right.
So that's why the de Sitter group is the one higher dimensional Lorentz group, which means that means that it's going to be in 4 dimensions, SO4. That's the de Sitter group.
Oh, okay. That's how. Right.
And you can actually work out what the you can work out what kinds of particles you can have in de Sitter by working out the representation theory of SO4.
Right. Right. Oh. Wow. Okay.
So there, that becomes relevant. Now, ADS is a very weird space. What happens in ADS, anti-de Sitter, instead of this, you throw in an additional minus.
Yeah.
See, that's a very weird space. It's not Minkowski space in 5D. It's some 2 time-like direction space. And in that space, you have SO 3,2. Right, that's going to be the group that preserves this. So that's the ADS group.
That's the ADS group. Oh, that's right.
And what's fascinating about all of this is that this also happens to be the conformal group in 4 dimensions. In 4-dimensional Minkowski space, the conformal group will be SO32. And then in 4-dimensional Euclidean space, in R4, the conformal group is SO41. What happens is that the conformal Euclidean vectors of either R4 or R31 can be realized as linear transformations, the symmetry transformations of a 1 higher dimensional space. It's called the embedding space. And then you can figure out all kinds of nice things about conformal going to this embedding space and playing that.
How does this aid or tie into correspondence in some way?
Yeah, well, you also discover that a lot of things that some of the entries of the dictionary in ADS-CFD they don't really have anything to do with ADS-CFD. They're just facets of this embedding space logic.
Oh, okay.
You see, so why am I saying that? I'm saying, let's take a 2-point function and you ask, you do your conformal field theory exercise. So you're going to do all kinds of complicated things to it to discover what its form is. You're going to do inversions, you're going to do special conformal transformations. They're all bizarre transformations. Those vector fields are not linear in terms of their coefficients in 4 dimensions, in R4. But if you go to the embedding space, they become linear. And in the embedding space, there you have to draw this pseudo-hyperboloid. You have to draw an ADS, essentially.
Yeah.
And there, on this ADS, they're just isometry transformations. It's the same exercise as what you would have if you were just looking at an ordinary quantum field theory. And then you say, well, where do I put these points? The points have to be on the boundary and so on. So you will discover that those exercises are not as exciting. So in some sense, it becomes important to understand the non-trivial content of this ADS-CFT correspondence. It's not just about these symmetry groups, right? So what's more, what's more is the locality structure. So any random CFT, you can think of its correlation functions and stuff as sitting somewhere in this embedding space. You can kind of figure out what's going on. But that doesn't mean that there's a duality there per se, right? It's not the kind of duality that people would like.
Yeah.
You would think that the true holographic dual is some highly quantum ADS space. So the strong version of the duality, you would say that there is actually a dual, but it's a quantum gravity theory. There's no semi-classical limit. It's just really hard to control. So it's about the locality structure. So how the locality structure is related. And then you start to ask some more careful questions about how these things are related. But you see, even if you don't care about holography at all, there's some use to those embedding spaces and these ADS or DS type structures. So that's an example of how higher dimensional symmetry groups enter into your, even if you're not doing higher dimensional field theory, you still have need for them.
Wow.
Yeah, and other fascinating things happen when you have these supersymmetric theories. And remember, I was telling you about this twist. Well, what the twist does is it ties together the isometry group of space and the internal symmetry group. You can mix these because of supersymmetry. And when you start to identify them, that's when you say you've really twisted the theory. Like when they actually start to coincide, that's when you say you've sort of twisted the theory.
Twisted the theory.
Okay. Yeah. That seems to be important for certain applications. Like if you want to put these theories on the lattice, it seems to be important that you know how to twist them.
Correspondence is nice. Okay. Okay, so this is where supersymmetry comes into the correspondence while mixing the internal symmetry groups and
not really. I mean, that's just something you could do.
Okay.
If you wanted to put it in the lattice, you'd say I could want to do that. If you say in the ADS-CFT correspondence, where does supersymmetry come in? There's no good reason for it to have to be there. It's just that in all known examples, it's there.
I see.
Because you can control, like you can calculate a lot of things, even a strong coupling with the supersymmetry.
Okay.
And that's why it's there. But it's not just supersymmetry that lets you control these theories, though. It's piece. So, when you talk about N equals 4 super Yang-Mills, that has much more going for it than just supersymmetry.
Right.
It's got super conformal symmetry. It's got integrability, all these kinds of things. Very hard to trace. So especially the things like integrabilities, though that really comes from, that really is a shadow of there being a string theory. What do I mean by that? It's the shadow of the fact that if I try to extrapolate the observables I'm trying to compute on the boundary with the bulk, I really need to draw classical string worldsheet. And the equations of motion for classical string worldsheets in ABS are integrable.
Yeah, they're
It's
right.
sort of like the bottom line of where all these techniques, how all these techniques work. And so that's just more than just supersymmetry. Although supersymmetry is very important for you to be able to start that exercise in the first place, because what are those fields? Like, usually the story begins with 6 scalars that they're really transforming in the R symmetry group of the extended n equals 4 supersymmetry. So you need that R symmetry, you need something that transforms in the R symmetry, and that's going to be, yeah. So directly it'll be relevant, but a priori there's no reason for it to have to have been there. And this is what say some people mean when they say, like, you could start thinking about holography from the root of Brown and Henon. They looked at asymptotic symmetry groups.
Right.
Discovered the conformal group. So there doesn't have to be supersymmetry. You could do that in general relativity. You don't have to do it in supersymmetry.
Right.
So yeah, it'll help you control things, but it's not a key ingredient.
Right.
But nobody knows what the key ingredient in holography really is. That's the
Right.
interesting question.
Yeah. Starting out reading these papers, that's one of the things, like
yeah, but I bet that you would think that it's important if you just read the papers, because what will happen is that you say that, okay, we have these grain constructions and all these such things, and they only really work because of supersymmetry.
Right.
That lets you keep track of whatever these things are. And anyway, so there's something magical about 16 supercharges. If you track where the 16 comes from, it comes from the supersymmetry algebra of 10D.
9 plus 1, yeah.
Yeah, so you basically keep an eye on, so why 16? 16 is half of 32. Why 32? 32 is 2 to the power 10 over 2 to the power 5, which is the dimension of the Clifford algebra in 10D.
Right.
So you need the Dirac spinors of 10D in order to be able to write down those generators of supersymmetry. And then if you have 2B, if you have chirality on top of that, you have a Majorana-Weil. So then you have chirality. Look at the Majorana-Weil spinors, and then you have 16, and then those 16 sort of descend. So you just compactify things, then but you still have that much. You still have that many fermions. You still have that many fermionic generators. So that 16 keeps descending. You can descend all the way down to 0 dimensions. So you can write a matrix model, right? With 16 superchargers. So that's called the IKKT model. So it has an action that looks like this. Come on. I J minus psi x. And now these gammas are really 10-dimensional gamma matrices. They're really gamma matrices that came from 10 dimensions. I just kept compactifying until I got back down to There's 10 xi's. These are 10 matrices. I runs from 0 to 9.
Okay.
And alpha and beta run from 1 to 16. Right? And you can define, I don't remember the supersymmetry transformations of this, but you can define supersymmetry transformations for x and psi. They transform into each other. So this is something called the IKKT model. It's the type 2B version of, let's say it's the T duo of a more famous matrix model, but it's matrix quantum mechanics. So it's not, it's a quantum mechanical system where you have X, piece of X, I minus. So when I say square, I mean that XIXJ contract with XIXJ top, but both commutative. So it's a very weird potential. So there's going to be a kinetic term for these fermions too. I don't remember how this works in slash. Okay, so it's going to be the analog of this, but then we only have one dimension. So this is going to be done in 0 d2, right? Alpha, delta. No. So you see the spinor indices and then these internal indices plus this term. So it's as though the IKKT model is like the potential term for the BFSS model.
Right.
So it's like the matrix model is the potential for matrix quantum mechanics. Don't trust me on the science. Definitely not on these powers here. This is a one-dimensional gauge theory. Why? Because there's a, when I write dt, I mean the time derivative plus some gauge potential. Anyway, this is the promised matrix model of the M theory or whatever you want to call it. So it really comes, again, it has 16 supercharges, it has allegedly some magic properties, it has a holographic duo, so there's all kinds of things it has going for it. Yeah, so these theories came from compactifying 10-dimensional super Yang-mills.
Right.
And the reason why you care about super Yang-mills is related to what compactifying, like, the architecture of brains, let's put it this way.
Right.
So low energy effective theory of these brains is our gauge theories. And so in 0 dimensions, you have the IKKT model. 2 dimensions, in 1 dimension, you have the BFSS model. In 2 dimensions, you have 2-dimensional super Yang-mills. And you can keep going that way. Each of these has 16 supercharges. Unfortunately, only when you get to 4 dimensions are any of them conformal. So n equals 4 super Yang-mills in 40, that's a conformal field. This is these are not conformal. So this BFSS model defines a dual, but it's not. You can't call it ADS-CFT. It's not a CFT.
Right.
So this is what happens when you try to stack these D3 brains. You can do other things though, and that's what the other story I told you related to this ABJ.
Right.
This is related to, but yeah. So this term, this is just fun. Like, I honestly think that none of this matters. I honestly think that this is an old story, which was beautiful, but it didn't live up to its promises. And there's things you definitely learn by delving into this, but the world has moved past it. So, but it's just fun, right? So where could this term come from? in dimensional reduction. Something you can wonder. It's just cute to look at this. So let's see. That's sort of the idea. So you start with the Yang-Mills Lagrangian. There's going to be some term that looks like so I mean AI AJ squared, but then really, these are matrices, right? Because this is a non-appealing case theory. And then really I want to square this guy. There's going to be a kinetic term. Kinetic term will drop out because I'm really looking at dimensional reduction. And so the potential term that sits, so the non-propagating part of this FF's term is where this XIXJ is coming from. It's like keeping only the zero modes of the higher dimensional gauge theory.
Right.
So yeah, that's why there's some relationship between these effective theories, brains, and higher dimensional gauge theories.
Okay. This is where it comes in.
And then you see, this is why you have this excess A naught here.
Yeah,
this guy broke away from the rest. Here I have 1 to 9 instead of 1 to 10. It broke away from the rest, and it has some dynamics.
Okay.
So you keep relaxing it, you just get more. So in higher dimensions, they start to take different forms.
Right.
If you compactify a gauge theory, you're not just going to get a gauge theory. You're going to get gauge theory, scalars, other systems.
Yeah.
Right? So very low dimensions will have only scalars. But maybe you have one gauge field, then you keep going.
Right.
And you see, supersymmetry is really a field space transformation. It's a transformation between fields, the bosons and the fermions. So, so long as you maintain the right number of fermions, you can keep transforming between the bosonic field and the fermions.
Okay. I think that was good. I'll just stop the recording here.
Okay.
Yeah.